Hi, welcome back, kiddos. I think we're on our last video of thermochemistry. Depends on how long this takes. And in this last one, we're going to talk about yet another way to determine the enthalpy for a chemical reaction. This time we're going to be using the given constants that are called heats of formation. Okay, the standard heat of formation is the change in enthalpy that accompanies the formation, this is key, of 1 mole of a substance from its individual elements, all at their standard or natural state, at what we call standard ambient. Ambient being 25 degrees Celsius, as opposed to the standard temperature and pressure we use with gases, which is 0 degrees Celsius. So the conditions are 1 atmosphere, 25 degrees Celsius. All right? Now, if we have an element in its natural state, which for zinc would be solid, which for mercury would be liquid, which for sulfur would be solid, which for hydrogen would be gas and diatomic. The standard enthalpy of formation of these elements in their natural state is 0. Now, what we're going to do, and I'm going to be honest, most formulas won't give you that N there for moles. I like to put it there because we're going to use our balancing or stoichiometric coefficients in this calculation. Now, most formulas are going to assume you know to do that, and so they'll leave that little mole off. But I want to really emphasize that to see if that helps you out a little bit. All right, so all we're going to do is we're going to add up the contribution from the products, and then we're going to subtract what the contribution was from the reactants. But first, you have to be able to write the balanced chemical equation. So we're going to use this for the combustion of sucrose. Remember, to combust means to react with oxygen. Now, if all we have are carbons, hydrogens, and sucrose is a solid, we're going to add oxygen. And if it's only hydrocarbons and or oxygens, we're going to make CO2. Now, sometimes you'll see this as H2O liquid, and sometimes you'll see in a combustion H2O gas. You need to pay close attention. All right, I've seen it written both ways. I'd prefer gas because with all the energy given off, you would think the water would vaporize, but you will see that as liquid in problems, so be careful. Now, if you balance this, you get a 12 here, a 12, and an 11. So what we're going to do is we're going to take our products, delta H for this reaction as written, is going to be the product. So I have 12 CO2 molecules. I'm going to plug in the value for CO2, minus 393.5. I have 11, that's the N in the formula I gave you, H2O, and I'm going to plug in the value that's given. And it's really important whether you pick the one that's liquid or solid or gas. They're different values, so you have to pay close attention. So those are my products. We added them up, and now we're going to subtract reactants. We have 1 sucrose, it's minus 2226. Now, I'm going to just make a silly point here. We have 12 oxygens, but that's oxygen gas, and elements at their natural state at standard ambient temperature and pressure, their enthalpy of formation is 0. So if you do that algebra, you should get minus 5158 kilojoules, which is logical that it'd be exothermic. Exothermic because it's a combustion. Combustion gives off heat, right? Okay, let's take a look at this next one. We're on a roll, I hope. Now this one is nitroglycerin, yet another chemical we're not allowed to buy. And in the table, we want to know the enthalpy change for 10 grams. Now, in this reaction, we're going to be finding first the enthalpy change for 4 moles. So the delta H for this reaction is going to be 10 times the water, which is minus 241.8, just getting it off the table, plus 12 times the carbon dioxide, minus 393.5. The oxygen is 0, and the nitrogen is 0. So I'm not going to bother writing them down. They're 0. That's why they're not given, because they're elements at their natural state at standard ambient temperature and pressure, and they're 0. 4 times my nitroglycerin plus, again, we have oxygen. So it's 0. So I'm not even going to bother. And there we go. Now that gives me minus 1172 kilojoules. But that was the kilojoules for 4 moles of the oops, I wrote down the answer to the next question. This was minus 5684 kilojoules. But that was for 4 moles. So if I take my 10 grams of nitroglycerin times 1 mole per the molar mass to moles use molar mass. Isn't it amazing how far you've come in a year? I'm so proud of you guys. 5,684 kilojoules. Now we calculated it for this reaction as written. So we're combining that stoichiometry we did earlier. So that's per 4 moles of nitroglycerin. So if I had 10 grams of nitroglycerin, that's going to be minus 62.6 kilojoules of energy. Okay? And again, this is an exothermic reaction. Now the next one, we have the production of nitric acid. Starts with the oxidation. Oxidation means to gain or lose electrons. In this case, oxidizing means to lose electrons. And so our enthalpy is equal to 6 times water. This time it's a liquid, so it's a different value given. And they'll be given. Plus 4 times my nitrogen monoxide. Minus my products, 4 times ammonia. And just to make a point, 5 oxygens, but elements at their natural state at standard ambient temperature and pressure are 0. And what we get is equal to minus 1172 kilojoules. Now, the only point, and that's negative, so that's exothermic. The only point I want to make out here is on your worksheets. Oh, I forgot to put in the value of ammonia. I wrote ammonia. I don't know why I did that. That was minus 46 in there. Okay, now the only thing that might be different is you might be given this value and you may ask to calculate one of the formations. So just make sure you're reading the question very carefully. But remember, with a flipped classroom, I'll be around to help you out. So until then, this is your best chemistry teacher signing off.